Okay, we have another equilibrium problem we're doing here, and it says a chemist is studying this following equation right here, and it gives an equilibrium constant at a certain temperature, and it says that nitrogen monoxide plus chlorine is going to give us NaOCl here, and it gives us our stoichiometry as well. So one thing I note is I say, geez, it's a pretty small equilibrium constant, meaning that I have many more, much more likely reactants than I do products. Okay, so that's one thing to note. So I always just quickly write my equilibrium equation. So that's going to be K sub P is going to equal the products. It's going to be the pressure of NaOCl, and that's going to be squared based on the stoichiometry, divided by the pressure of NO, which is also going to be squared, times the pressure of Cl2, which is just going to be raised to the first power. Okay, and so my problem is asking me find the equilibrium pressure of NaOCl. Okay, well, I can start off using my ice tables, and so I'm going to write initial change equilibrium, and I like following the chemical equation. So this is going to be NO, this is going to be Cl2 up here, and finally we're going to have NaOCl. Okay, well, I'm trying to find NaOCl, and so I don't have any of that at the beginning, and the change, I'm just going to set that equal to x, just to make my life and my math easier. I'm going to make that equal to x. Well, the problem says that I start off with 11 atmospheres of NO, and I start off with 12 atmospheres of Cl2. So I have to look at the stoichiometry here to find out what that change is going to be. Well, because I set NaOCl equal to x, then what I can do is I can take the coefficient out in front and divide it by the coefficient in front of the NaOCl to get my changes. So I know that 2 divided by 2 is 1, so this is going to equal 1x. That NO is going to go down by x, just as NaOCl is going to go up by x. Alright, so that's going to be a minus x. And then I also know that with Cl2 that's going to go down. So I take the coefficient out in front, which is 1, divided by that 2 in front of NaOCl. 1 over 2 is 1/2. And so this is going to go down by 1/2 x, which means in the end I have 11 minus x at equilibrium, 12 minus 1/2 x at equilibrium, and just x at the NaOCl at equilibrium. Okay, well, I can go ahead and plug these equilibrium concentrations into my equation up here, and so that is going to tell me that 4, which is K sub P, times 10 to the negative 6 is going to equal the concentration of NaOCl, which is x squared, I'm just getting that from right up here in that equation, divided by the nitrogen monoxide pressure is going to be 11 minus x squared times 12 minus 1/2 x. That's raised to the first power. Well, I can already see that's some math. I just don't want to deal with it if I don't have to. And so I could, because this K sub P is so small, I'm going to make the assumption that I can just ignore it. Okay, because that x is going to be so small. And so anytime I add or subtract x, because I'm going to assume that x is really small, then it really has no effect. Okay, so I know that 11 minus something really small is really close to 11 still. So I'm just going to ignore that x. And it might not be a good assumption, but we'll find that out later. And I'm going to ignore this x term right here because this is so teeny, I'm assuming, that I really still have 12 left. Okay, so let's rewrite that equilibrium equation. So it's 4 times 10 to the negative 6, and that's going to equal x squared divided by 11 squared, because I just ignored that x, times 12, because again I ignored that x. Okay, this is some math that I can probably do a little bit better, and so when I do rearrange this and do the algebra, then I am left with 5.81 times 10 to the negative third is going to equal x squared. Well, I can take the square root of both sides, and that will leave me that x is going to equal 0.0762. These are going to be atmospheres, because that's what x is in units. It asked me for 1 sig fig, so x is going to be equal to 0.08 atmospheres at 1 sig fig. Okay, well, we ignored that x. Okay, we ignored the change in x in our math up here. Okay, and so the question is that a valid assumption? Well, we use a 5% rule, that if I take this 0.08 and I divide it by the starting amount, let's just choose 11 right here, is that number going to be less than 5%? When I convert that to a percentage, and you'll find that absolutely it is less than 5%. So this is a valid assumption. And so I can put this into my LX, and I feel pretty good that it's going to be right. So again, what do? Is I set up my equilibrium equation. I set up my ice tables correctly right here. In this case, I'm using fractions. I know sometimes we struggle with that, but hopefully I showed you the way to find out what those fractions are. When we set x, NOCl, equal to x, we're going to have to use fractions. I then take my equilibrium concentrations, plug it right back into this equation, which I did down in this quadrant down here, and I just ignore the x. I assume that I can, and the reason I assume I can is because k sub p is really, really small, and anytime I add or subtract something small, it's close to the same. When I make those assumptions, then I do the algebra, and I'm left with this x. So these are doable, I think, for you.